In today's video, we overclock the Intel Core i7-12700K processor all the way up to 5.4 GHz using the EK Quantum MSI MPG Z690 Carbon EKX motherboard. The Z690 Carbon EKX is the fourth model in the Carbon EKX family, following the Z490, Z590 and X570S. It uses the MSI MPG Z690 Carbon motherboard as the base, and adds an EK Quantum monoblock on top of it. In addition to overclocking the Core i7-12700K processor, in this video we'll also have a closer look at the history of MSI's automatic overclocking tools, as well as have a deep dive in the Alder Lake VF curve. Alright, there's a lot to go through, so let's get started. The Intel Core i7-12700K is part of the 12th generation Intel Core processor lineup. Intel Alder Lake has an all-new core design with performance hybrid architecture featuring performance cores and efficient cores. It's built on the Intel 7 process technology, formerly known as 10nm enhanced superfin. The overclockable K-SKU processors again come in three flavors: Core i9, Core i7 and Core i5. Each of the three flavors has a K and KF variant. The only difference between the two variants is that the KF comes without integrated graphics. The Core i7-12700K processor has 8 P-cores and 4 E-cores with a total of 20 threads. The base frequency is 3.6 GHz for the P-cores and 2.7 GHz for the E-cores. The maximum single-core boost frequency is 4.9 GHz for the P-cores and 3.8 GHz for the E-cores. The maximum all-core boost frequency is 4.7 for the P-cores and 3.6 GHz for the E-cores. The favored P-cores can boost 100 MHz higher to 5 GHz. The processor base power is 125 watt and the maximum turbo power is 190 watt. In this video, we will cover 4 different overclocking strategies. First, we increase the performance headroom by unleashing the Turbo Boost 2.0 limits and enabling XMP 3.0. Second, we test out MSI's Game Boost one-click overclocking button. Thirdly, we use MSI's turbo ratio offset feature to further increase the performance. Lastly, we do manual overclocking to get the most performance out of our system. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. Along with the Intel Core i7-12700K processor and EK Quantum MSI MPG Z690 Carbon EKX motherboard, in this guide we will be using a pair of 16GB Hynix DDR5-6200 memory sticks, an RTX 2080 Ti graphics card, a 512GB M.2 NVMe SSD, a WD Black SN850 NVMe SSD, a Seasonic Prime 850W Platinum power supply, the Elmo Labs Easy Fan controller, and EK Quantum water cooling. All this is mounted on top of our favorite open bench table. The cost of the components should be around $4,370. We place the WD Black SN850 SSD in the top M.2 drive, which is cooled by the EK monoblock. We use it exclusively to measure the M.2 drive temperature during our stability testing. I covered the Elmo Labs EFC in a separate video on this channel. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC. Then I use the low-high setting to map the fan curve from 25 to 40 degrees water temperature. This is used for all overclocking strategies. In today's video, we are pairing the Intel Core i7-12700K processor with the EK Quantum MSI MPG Z690 Carbon EKX motherboard. The Z690 Carbon EKX is the fourth product in the EK MSI collaboration range. MSI has put a lot of effort into upgrading the feature list of the Z590 series motherboards to deliver more on Z690. I won't go into too much detail, but upgrades include of course DDR5 support, improved VRM design, improved PCB materials, more M.2 slots, and so on. Our main interest is of course the EK monoblock, as that one will be cooling down our CPU. Even though the monoblock on the Z690 might look very similar to the ones on the previous generation Carbon EKX motherboards, there's a couple of differences. First, In addition to cooling the CPU and VRM components, the Z690 Carbon EKX monoblock now also covers the top M.2 slot. According to EK's website, the EK-M.2 active contact cooling is designed to ensure your main drive will not throttle under any circumstance. This is supported by MSI's internal test data, showing a significant improvement from 91 degrees Celsius to 31 degrees Celsius for the M.2 drive temperature. While I will include an M.2 drive test in my stress test scenario, I won't do any specific testing of the M.2 cooling performance. I'll leave that up to the professional M.2 reviewers to figure out. Second, the cooling engine is updated to support the specific Alder Lake CPU characteristics. Third, it's the first monoblock on the market which is compatible with the EK Matrix 7 industry standard. This will be particularly good information for whoever is out there building custom loop systems. However, it has a minimal impact on test bench systems like mine. If you want to learn everything about the MSI Z690 range, feel free to check out the 2-hour live stream they did on their MSI Gaming YouTube channel. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. It is the first time that we use the Atto disk benchmark in a SkatterBencher video. And the main reason is of course because the Z690 Carbon EKX monoblock also cools the top M.2 drive. During our 30-minute Prime 95 stability testing, we will periodically run an Atto benchmark workload and record the peak M.2 drive temperature. Our configuration for the Atto disk benchmark is as follows. I'm not a storage expert, so if you have any idea of what would be a better benchmark or stress test, please do let me know in the comment section below. The first thing we must do before we start any overclocking is check the performance at default settings. Please note that the Z690 Carbon EKX out of the box unleashes the Turbo Boost 2.0 parameters. So to check the performance at default settings, we first have to go into the BIOS and enter the overclocking settings menu, enter the advanced CPU configuration submenu, set long duration power limit to 190, set long duration maintained to 56, set short duration power limit to 190, then save and exit the BIOS. Here is the benchmark performance at stock. Here are the 3DMark CPU profile scores at stock. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 4663 MHz and the average CPU E-core clock is 3591 MHz with 1.176 volts. The average CPU temperature is 71 degrees Celsius, the average VRM temperature is 46 degrees Celsius, and the maximum M.2 temperature is 52 degrees Celsius. The average CPU package power is 190 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 4689 MHz and the average CPU E-core clock is 3591 MHz with 1.19 volts. The average CPU temperature is 72 degrees Celsius, the average VRM temperature is 46 degrees Celsius, and the maximum M.2 temperature is 51 degrees Celsius. The average CPU package power is 188 watts. Now let us try our first overclocking strategy. However, one more thing. Make sure to locate the clear CMOS jumper. Shorting the clear CMOS jumper will reset all your BIOS settings to default. This is useful in case your system does not boot up after overclocking or if you want to start your BIOS configuration from scratch. However, it does not delete any of the BIOS profiles previously saved. The Clear CMOS button is located at the bottom right of the motherboard. In our first overclocking strategy, we simply make use of unleashing the Turbo Boost 2.0 parameters and XMP 3.0. Turbo Boost 2.0 is an Intel technology that's been around since 2010 on Sandy Bridge. Simply put, Turbo Boost 2.0 allows the processor to operate above base frequency if there's sufficient power, current, and thermal headroom. The obvious advantage is improved system performance in both multi-threaded and single-threaded applications. The Turbo Boost algorithm works according to a proprietary EWMA formula. This stands for exponentially weighted moving average. There are three parameters to consider: PL1, PL2, and tau. Power limit 1 or PL1 is the threshold that the average power will not exceed. Historically, this has always been set equal to Intel's advertised TDP. Very importantly, PL1 should not be set higher than the thermal solution cooling limit. Power limit 2 or PL2 is the maximum power the processor is allowed to use for a limited amount of time. Tau is a weighing constant used in the algorithm to calculate the moving average power consumption. If the average power consumed is higher than PL1, the CPU will reduce the CPU frequency. Obviously, Turbo Boost 2.0 is available in Alder Lake as it's the main driver of performance above the base frequency. A major difference between Alder Lake and any previous Intel Core processor is that, at least for the K-SKU CPUs, PL1 is by default equal to PL2. This is very different from before, where PL1 would equal the TDP and PL2 would range from 200 to 250 watts. This effectively means that Intel has enabled near unlimited peak turbo by default. For the 12700K, the maximum power limit is set at 190 watts. The maximum performance is therefore entirely limited by the capabilities of your cooling solution. If your cooling solution is insufficient, then the processor will reduce the operating frequency at the maximum allowed temperature, or TJ max. For Alder Lake CPUs, that's at 100 degrees Celsius. On MSI motherboards, there's an easy CPU cooler tuning option that allows you to unleash the Turbo Boost power limits. Simply set the option to water cooler and enjoy the maximum performance. On first boot, the BIOS will pop up a menu to select the CPU cooler type. On the Z690 Carbon EKX, water cooler and its associated unlocked Turbo Boost power limit is selected. Intel Extreme Memory Profile, or XMP, is an Intel technology that allows you to automatically overclock the system memory for improved system performance. It is an extension of the JEDEC standard that allows memory vendors to program higher frequency and better memory timings onto the memory sticks. Intel Extreme Memory Profile 3.0 is a new XMP standard for DDR5 memory. It is largely based on the XMP 2.0 standard for DDR4, but has additional functionality. The XMP 3.0 standard is designed with 6 sections. One global section describes the generic data which is used across the profiles. The 5 other sections are designed for 5 profiles respectively. Profile 1 is meant for the performance profile. This is the standard XMP as we know it. Profile 2 is designed for the extreme settings. This could be a higher frequency at a higher voltage. Profile 3 is designed for the fastest settings. This could be tighter timings at higher voltage. Profiles 4 and 5 are rewritable and meant for user custom settings. There's a lot more to the new XMP 3.0 standard, but it falls outside of the scope of this overclocking guide. However, by the time this video goes up, I should already have a more detailed video up on this channel. So check that one out if you want to have more information. Upon entering the BIOS, in advanced mode, click XMP Profile 1. Enter the overclocking settings menu. Under CPU cooler tuning, ensure the option water cooler PL1 4096 watt is selected. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. As expected, we see the largest performance difference in multi-threaded applications which were previously constrained by the maximum power of 190 watt. We see up to 5.31% performance increase in Geekbench 5 Multi. In single-threaded benchmark applications, the performance improvement is negligible. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 4689 MHz, and the average CPU E-core clock is 3591 MHz, with 1.212 volts. The average CPU temperature is 80 degrees Celsius, the average VRM temperature is 49 degrees Celsius, and the maximum M.2 temperature is 53 degrees Celsius. The average CPU package power is 219 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 4689 MHz, and the average CPU E-core clock is 3591 MHz with 1.191 volts. The average CPU temperature is 72 degrees Celsius, the average VRM temperature is 46 degrees Celsius, and the maximum M.2 temperature is 52 degrees Celsius. The average CPU package power is 188 watts. In our second overclocking strategy, we simply make use of the one-click overclocking feature called MSI Game Boost. Game Boost is a unique feature for MSI and has been on motherboards for quite a while, and it offers a simple way to get extra performance with 1 second of work. Simply put, as per MSI, Game Boost enables 1 second overclocking, boosting performance so you can achieve more frames per second. The history of MSI Game Boost can be traced back all the way to mid-2007 when Intel launched their P35 Express chipset for LGA 775 processors. The feature wasn't called Game Boost back then, but the function was very similar, a one-step process to achieve better system performance. Browsing through the manual of the MSI P35 Neo 2-FR motherboard, we find on page 2-19 a feature called Hardware Overclock FSB Jumpers. By configuring these jumpers in different positions, you can change the front-side bus frequency between 200, 266, and 333 MHz. This in turn increases the CPU core frequency. About 1 year later, around June 2008, Intel launched the P45 Express chipset also for the LGA 775 processors. MSI retained the OC jumper as a way to increase the front-side bus frequency from 266 MHz to 400 MHz, though it was rebranded as Rapid Boost. It wasn't until the launch of the Intel X58 chipset for LGA 1366 processors that MSI switched from the old-fashioned jumpers to the more user-friendly switches. The Easy OC switch, implemented on motherboards like the X58 Eclipse SLI, was still the one-step overclocking tool that allows users from any pedigree to increase the performance of their system by overclocking. Undoubtedly well intended by MSI, but perhaps a thorn in the eye of Intel, MSI's marketing slides point out that the Easy OC switch can turn your $300 Core i7-920 into a $1,000 Core i7-965. Not all reviewers agreed with MSI. Steve Walton from TechSpot, nowadays at Hardware Unboxed, found the feature to be, quote, rather pointless. Regardless, MSI continued its mission to provide novice users with an easy way to overclock the CPU and improve system performance. In September 2009, Intel launched the P55 chipset for LGA 1156 processors, and MSI came with something totally new, OC Genie. MSI OC Genie is a hardware-based automatic overclocking tool that relies on an actual chip on the motherboard to overclock the CPU. In a press release, MSI said that they used their 20-year R&D experience to develop the new Easy OC technology, OC Genie. Combining OC Genie's press button and dedicated overclocking processor, no complicated setup and professional overclocking skills are required to boost up to 45% performance in 1 second. By just the press of the OC Genie button, the OC Genie processor automatically detects the best overclocking settings of CPU, memory, and integrated graphics. Furthermore, OC Genie also adjusts the voltage settings to ensure stability. Reading through motherboard reviews from the time, OC Genie seems to have been very well received. Guru 3D extensively tested OC Genie with the MSI P55 GD80 motherboard, and by the press of a button, managed to increase the Core i7-870 CPU frequency by 800 MHz from 2.93 GHz to 3.74 GHz. They also indicate this was a 100% stable overclock. MSI OC Genie eventually also carried over to some X58 motherboards like the MSI Big Bang X58 X-Power, as well as in BIOS form appeared as OC Genie Lite on certain AMD motherboards. It got a little bit confusing at the time, as some AMD motherboards like the MSI 890 GXM-G65 featured both OC Genie Lite in the BIOS and an easy OC switch on the motherboard itself. Oh yeah, that's a forum post by the same top PC who now works for MSI. Moving forward, when Intel launched the P67 chipset for LJ1155 Sandy Bridge processors in 2011, MSI introduced OC Genie 2. The second generation of OC Genie was pretty similar to the first generation, but better, as MSI claims now even your girlfriend can get extra performance. Not entirely sure that line of thought would be possible these days. Sandy Bridge fundamentally changed the way overclocking is done. Whereas before Sandy Bridge, CPUs could be overclocked by increasing the base clock frequency, on Sandy Bridge, overclocking was restricted exclusively to the K-SKU CPUs with unlocked CPU multipliers. Undeterred by this limitation, MSI claimed OC Genie 2 would increase the clock frequency of a Core i5-12700K by 900 MHz from 3.3 GHz to 4.2 GHz. Many reviewers had a go at overclocking with OC Genie 2, including a young Linus Tech Tips. With the press of a single button, young Linus managed to overclock his Core i7-12700K to 4.2 GHz. In April 2012, Intel launched the successor to Sandy Bridge, Ivy Bridge, with its Z77 chipset. MSI's leading mainstream overclocking board was the Empower, which also featured OC Genie 2. Young Linus again showed off the overclocking capabilities of the OC Genie 2 feature, demonstrating a
30+% improvement.
The OC Genie 2 feature was also present on a wide range of MSI X79 motherboards, allowing media such as PC Perspective to achieve an overclock of 400 MHz on a Core i7-3820 with a base frequency of 3.6 GHz. Then came Haswell and its Z87 chipset in 2013. Here's where MSI took the automatic overclocking tool in a fresh direction. There are several changes to how OC Genie works. First, we jump straight from OC Genie 2 to OC Genie 4. Second, the function is now available both in the form of the traditional button as well as a virtual OC Genie in the BIOS. Third, an OC Genie mode switch provides two gears which determine how aggressive OC Genie pursues the overclock. Based on AnandTech's coverage of the MSI Z87 X-Power motherboard, Gear 1 would overclock the Core i7-4770K to 4 GHz, whereas Gear 2 would overclock that same CPU to 4.2 GHz. The Haswell refresh and accompanying Z97 chipset wasn't much of a change from the products launched 1 year earlier. MSI pretty much adopted the same OC Genie 4 feature set. Also, on the HEDT X99 platform, the implementation was the same, at least on the first generation launched in 2014 together with the Haswell E processors. Then, in August 2015, something changed. When Intel launched the 6th generation Core processor codenamed Skylake and its Z170 chipset, MSI put the OC Genie back in its bottle and introduced the Game Boost knob. Game Boost's function is not too different from OC Genie in that it still aims to provide an easy way for novice users to overclock their CPU. When researching the Game Boost knob, I came across an interesting story on the origins of this physical knob. The long story short is that AnandTech's Ian Catress claims he's responsible for MSI's decision to bring this knob to market. As his story goes, the knob originally featured on development versions of MSI's Z170 motherboards and was used by the engineers to do specific things like loading OC profiles, safe booting, memory safe booting, applying specific settings, and so on. Ian alleges he convinced MSI to repurpose this knob or dial as a multi-step overclocking function. The Z170 Game Boost knob is an 8-step dial that goes from 0 to 11. Each step has a predefined base clock frequency, CPU ratio, and voltage, which lifts the frequency of a Core i7-6700K from 4300 MHz at step 1 to 5000 MHz at step 11. The virtual BIOS version of Game Boost offered no multi-step approach, but a binary on-off for the Core i7-6700K. Game Boost On means running at 4.4 GHz, which is equal to Game Boost Step 2 on boards with the 8-step dial. MSI adopted the Game Boost knob on the second generation X99 motherboards, which launched with the Broadwell E processors. We even have a video up on this channel where we overclock a Broadwell E Core i7-6950X processor using the MSI Game Boost dial on the MSI X99A Gaming Pro Carbon motherboard. By now, the virtual Game Boost knob in the BIOS offered the same features as the physical dial on the motherboard, with 8-step multi-level overclocking from 0 to 11. And here's where the Game Boost knob sort of continues to live on. The high-end motherboards have this 8-step dial up to 11, as well as a virtual version of this multi-step overclocking tool, and the mid-end to low-end motherboards just have the on-off button in the BIOS. On the Z270 motherboards, you'll find automatic Game Boost overclocking for the 6th gen and 7th gen processors. On X299 motherboards, which still feature the Game Boost dial, it no longer bears the intrusive bright red color, but is replaced by a black dial. The 8-step overclocking up to 11 persists. On the Z390 motherboards, the button still goes up to 11 and changes the CPU ratio as well as CPU voltage. By this time, AMD had risen from the bulldozer ashes and also gets their Game Boost function. On the X370 X-Power Gaming Titanium, we find the same bright red button as on the high-end Intel motherboards, and we find the same 8-step overclocking levels up to 11. We find the less intrusive black dial version on the MSI X470 Gaming M7 AC, with more overclocking up to 11. We also find the black dial on the X570 Godlike, launched in the summer of 2019. In 2020, the MSI Game Boost knob disappeared from the high-end MSI motherboards, and we get the same Game Boost implementation across the entire product stack. That is, a single BIOS button that either enables or disables the Game Boost function. The function is also the same across the product stack. That is, you get one turbo ratio extra over default when you enable Game Boost. And that's where we find ourselves right now. Enabling Game Boost on the Z690 Carbon EKX lifts all turbo ratios by +1 for both P cores and E cores. In addition, it also sets an AVX negative ratio offset of -3. This results in a maximum boost frequency of 5.1 GHz. Upon entering the BIOS, in advanced mode, click the Game Boost button. Click XMP Profile 1, then save and exit the BIOS. We reran the benchmarks and check the performance increase compared to the default operation. The performance increase after a +1 ratio bump is not spectacular, but we do see some solid gains in multi-threaded benchmarks in particular. The largest increase is +8.78% in AI benchmark. Despite the use of an AVX negative ratio offset, we don't see any major implications on the benchmark result. However, we do see a frequency reduction when using Prime 95 with AVX. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 4615 MHz, and the average CPU E-core clock is 3691 MHz with 1.2 volts. The average CPU temperature is 77 degrees Celsius, the average VRM temperature is 48 degrees Celsius, and the maximum M.2 temperature is 52 degrees Celsius. The average CPU package power is 211 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 4788 MHz, and the average CPU E-core clock is 3691 MHz with 1.228 volts. The average CPU temperature is 77 degrees Celsius, the average VRM temperature is 47 degrees Celsius, and the maximum M.2 temperature is 52 degrees Celsius. The average CPU package power is 205 watts. In our third overclocking strategy, we make use of MSI's unique turbo ratio offset feature. Turbo ratio offset allows us to increase the turbo ratios over the default configuration by a certain amount of bins. This is very helpful as it allows you to set a dynamic overclock without having to dig too deep in the BIOS settings. We'll also make use of another Intel feature called Adaptive Voltage Mode. Adaptive Voltage Mode is best suited for a dynamic overclock, which we'll set using the turbo ratio offset feature. In order to figure out which voltage to set for the Adaptive Voltage Mode, we'll also take a closer look at this CPU's VF curve. On Alder Lake CPUs, the voltage for the CPU P-cores, E-cores, and ring are all driven by a single voltage rail called VCC-IA. That means there's only one voltage that can be applied to each of these parts in the CPU. The voltage can be set in two ways, adaptive or override. Override mode specifies a single static voltage across all ratios. It is mostly used for extreme overclocking purposes, where stability at the very high frequencies is the only consideration. Adaptive mode is the standard mode of operation. In adaptive mode, the VF curve used is generated automatically by the CPU and covers the CPU ratios from the lowest supported ratio to the default maximum turbo ratio. In the case of the 12700K, that's from 8x to 50x. VF curve stands for voltage frequency curve. The VF curve determines which voltage the CPU should set for a certain frequency. We'll do a deep dive in the topic of the CPU VF curve in a couple of minutes. But first, a couple more things about configuring an adaptive voltage in the BIOS. The adaptive voltage set in the BIOS is mapped against what's called the OC ratio. When you leave everything at default, the OC ratio is the default maximum turbo ratio plus 1. In case of the 12700K, that ratio is 50x, which is the Turbo Boost Max 3.0 frequency. So, the default OC ratio is 50 plus 1 equals 51x. When you manually overclock, the OC ratio is the highest ratio you configure across all the various settings and options. There are very specific rules that govern how an adaptive voltage is set. A. The voltage set for a given ratio n must be higher than or equal to the voltage set for ratio n-1. For our 12700K, the VF curve is defined up to 50x, so the OC ratio is 51x. If the voltage for 50x is 1.35 volt, then setting the adaptive voltage, which is mapped against the 51x ratio, to anything below 1.35 volt is pointless. Since 50x is specified to run at 1.35 volt, 51x will always run at 1.35 volt or higher. Usually, BIOSes will allow you to configure lower values. However, the CPU internal mechanisms will override your configuration if it doesn't follow the rules. B. The adaptive voltage configured for any ratio below the OC ratio will be ignored. Take the same example of the 12700K, which is specified to run 46x at 1.18 volt. If you try to configure all cores to 46x, use adaptive voltage mode, and set 1.3 volt, the CPU will ignore this because it has its own factory fused target voltage for all ratios up to 50x and will use this voltage. You can only change the voltage of the OC ratio, which, as mentioned before, on the 12700K is 51x and up. For ratios between the OC ratio and the next highest factory fused VF point, the voltage is interpolated between the set adaptive voltage and the factory fused voltage. Returning to our example, our 12700K is specified to run 50x at 1.35 volt, and let's say we manually configure the OC ratio to be 54x at 1.425 volt. Now, the target voltage for ratios 51x, 52x, and 53x will be interpolated between the VF point 50x at 1.35 volt and our OC ratio 54x at 1.425 volt. So, in conclusion, the adaptive voltage set in the BIOS is mapped against the OC ratio. The OC ratio is the highest ratio configured for the CPU across all settings, including by core usage, per core ratio limit, and OCTVB. The voltage for ratios lower than the OC ratios are set either by its factory fused VF point, or, if there is no VF point, interpolated between the next and previous VF point. In all my SkatterBencher videos, the final OC strategy is always a manual overclock. In that OC strategy, I show you the settings that worked for me, and I explain the different tools that I use to set that maximum overclock. But rarely I dig into how to figure out your maximum stable overclock. In this video, I want to do it a little bit different. So I want to cover how to find at least the baseline for your manual overclock by using the CPU VF curve. The VF curve, or voltage frequency curve, determines the relationship between the operating voltage and the operating frequency. Every Intel CPU has a factory fused VF curve. Let's go into the MSI BIOS and have a look. When you enter the BIOS, go to the overclocking settings menu. Here you will find a long list of settings that allow you to manually configure your CPU. You can see that the P-core ratio is currently set at auto, and auto is 3600 MHz. When scrolling down to the voltage section, you will find an item called CPU core voltage. Next to the item name, we can see a voltage indicator and, of course, the setting. The voltage indicator says 1.164 volt. If you look at the top of your screen, you can find the same value there as well. This voltage indicates the current voltage for the CPU cores. We can use this indicator to figure out what is the factory fused VF curve of this 12700K. For example, we can manually set the CPU P-core ratio to 49x, reboot, and check the voltage again. As you can see, the voltage increased and is now 1.304 volt. If we do this for every CPU ratio, we will figure out what is the VF curve of this CPU. Well, sort of. As per usual, it's not as simple as it may seem. To understand why, we first need to study the Alder Lake CPU design more closely. In this short theory lesson, we will cover 4 topics: VCC-IA voltage rail, VID requests, VCC sense versus socket sense, and Intel VF curve versus motherboard auto rules. The first thing we need to take a look at is the Alder Lake voltage topology. If we only consider the Alder Lake CPU and disregard the Z690 chipset, there are a total of 7 different voltage inputs for the Alder Lake platform. The voltage we are concerned with is called the VCC-IA. IA stands for Intel architecture and is the collective term for all Intel CPU cores. Therefore, logically, the VCC-IA powers both the P-cores and E-cores. It also powers the ring. As this is a single voltage rail, all parts powered by this rail will run at the same voltage. The voltage for the VCC-IA rail can be configured in 2 main ways: override mode and adaptive mode. For this segment, we will ignore override mode and only work with adaptive mode. As I mentioned before, the VF curve stands for the voltage frequency curve and describes the relationship between the operating frequency and operating voltage. A lot of parts inside your CPU have a VF curve, including every P-core, every E-core cluster of 4 cores, the ring, and the integrated graphics. We can ignore the integrated graphics for now, as this is powered by another voltage rail called VCC-GT. For the 12700K, there are a total of 10 relevant VF curves for our VCC-IA voltage rail, 1 for each of the 8 P-cores, 1 for the E-core cluster of 4 cores, and 1 for the ring. So how does the CPU decide which voltage to set? Actually, that's pretty straightforward. The VCC-IA voltage is the highest among all the requested voltages. For example, if the P-core requests 1.3 volt for 4.9 GHz, the E-core requests 1.2 volt for 3.9 GHz, the ring requests 1.1 volt for 3.8 GHz, then the VCC-IA voltage is the maximum of 1.3, 1.2, and 1.1, so 1.3 volt. Or if the P-core requests 0.9 volt for 3.4 GHz, the E-core requests 1.2 volt for 3.9 GHz, and the ring requests 1.1 volt for 3.8 GHz, then the VCC-IA voltage will be the maximum of 0.9, 1.2, and 1.1, so 1.2 volt. Or if the P-core requests 0.9 volt for 3.4 GHz, the E-core requests 1.0 volt for 3.3 GHz, and the ring requests 1.1 volt for 3.8 GHz, then the VCC IA voltage will be the maximum of 0.9, 1.0 and 1.1, so 1.1 volt. As you can see, this can lead to some interesting situations where overclocking the E-cores or ring can lead to overvolting the P-cores for a certain frequency. This was in fact a very real challenge with Rocket Lake. Returning to the BIOS, we can now understand what the voltage indicator next to the CPU core voltage really means. This is the current VCC IA voltage, which is determined as the highest voltage as requested by the active CPU P-cores, E-core cluster, and ring. The keyword in that last sentence is active. To make a long story short, an Intel CPU has power-saving features that allow certain parts of the CPU to shut down when not in use. On Alder Lake, each P-core and E-core cluster has a power gate which allows for enabling or disabling of the cores depending on the current system load. From observation, it seems that the MSI BIOS is loading one P-core and none of the E-cores. This will be important information when we try to figure out the E-core VF curve later on. But for now, let's just focus on the voltage indicator and remember that the VCC IA voltage drives the P-cores, the E-cores, and the ring. The next topic we must study more closely is how the voltage is configured in adaptive voltage mode. We already know that there's a multitude of VF curves inside the CPU that drive the VCC IA voltage rail. But that's not the full story on how voltage is set. Generally speaking, in adaptive voltage mode, there are 3 steps to how the voltage is set. In step 1, the motherboard's BIOS tells the processor the current load line characteristics via AC-DC load line values. The AC-DC load line characteristics are a way for the motherboard to inform the CPU about its specific VRM design. This is highly important in situations where the CPU goes from idle to load and there's a voltage droop. Voltage droop is the difference in voltage between idle and load. If the VRM has better components and design, we expect less of voltage droop. If the components and design are worse, we can expect a greater voltage droop. Using the AC-DC load line configuration, the motherboard BIOS can inform the CPU about the quality of the VRM design. With this information, the CPU can then determine whether it should request the voltage according to its VF curve or make any adjustments. In step 2, the CPU will issue a voltage request to the motherboard voltage controller using a VID. This VID is based on a variety of parameters, including the factory-fused voltage frequency curve, any manually set voltage offset or VF point offset, the AC-DC load line configuration, voltage reductions triggered by the thermal velocity boost technology, and voltage increases triggered by the AVX voltage guard band. For those who like equations, the requested VID can be expressed as follows. The CPU will also read back the VID to check if it matches the requested VID. If the readback VID is lower than the base VID, then the CPU will dynamically increase the requested VID. In summary, the VF curve provides the CPU with a baseline VID. However, in order to request a VID to the voltage controller, the CPU takes into account a multitude of different parameters. This will be important when we try to figure out the baseline VID later on when we figure out the VF curves. In step 3, the VRM controller will output the voltage. The VRM load line determines the final effective voltage. A weaker load line will worsen the V-droop, while a stronger load line will lessen the V-droop. In addition, the VRM load line will also impact any undershoot or overshoot. Undershoot and overshoot are temporary voltage spikes when transitioning from idle to load and load to idle. To sum up, there are many factors that determine the actual voltage of your CPU core. The factors include the factory-fused VF curve, the VRM component design and configuration, any AVX guard band, and the thermal velocity boost voltage optimizations. We can demonstrate how each of these factors impact the CPU core voltage. I set up the BIOS with the following settings: all P-cores at 49x, disable the E-cores, and set the ring ratio to 8x. This ensures that the VCCIA voltage will be determined by the P-core voltage request. Then I set the CPU core voltage mode to adaptive plus offset mode, and I make sure the following base settings are configured. Voltage offset 0 mV, CPU light load control mode 12, this is the AC-DC load line configuration, TVB voltage optimizations disabled, AVX guard band scale 128, this is the default value, CPU load line calibration control to mode 4. We can see the following. Our baseline settings give us a voltage of 1.446 volt for a CPU P-core ratio of 49x. When we add a plus 50 mV adaptive voltage offset, we see that the voltage increases to 1.504 volt. When we change the AC-DC load line settings from mode 12 to mode 1, the voltage decreases to 1.3 volt. When we change the AVX guard band scale factor to 0, nothing happens. That's because the BIOS doesn't run AVX instructions, so the guard band isn't active. When we enable the thermal velocity boost voltage optimizations, the voltage decreases to 1.348 volt. When we change the CPU VRM load line from mode 4 to mode 8, the voltage decreases slightly to 1.434 volt. For science, I also checked the worst case and best case scenarios, and here are the results. So, depending on the configuration of the BIOS settings, for 4.9 GHz, we get a voltage between 1.208 and 1.688 volt. Not only does this serve as a great example of why it's difficult to compare CPU voltages with other people's systems, it is also valuable information for when we eventually get to figure out the CPU's voltage frequency curve. Viewers who are paying attention will have noticed that I've selected Socket Sense as CPU core voltage monitor. While it doesn't really impact what we're trying to do in this guide, I do want to spend a couple of minutes explaining the difference between VCC Sense and Socket Sense. Do note that I'm not an expert on the matter, so best to check out, for example, Buildzoid if you want to have more detailed information. The long story short is that the difference between VCC Sense and Socket Sense is where the voltage is measured. The VCC Sense measures the voltage directly on the CPU die, whereas the Socket Sense measures the voltage on the motherboard. The key difference is that the VCC Sense factors into account the resistance of the CPU socket and CPU substrate, whereas Socket Sense does not. Generally speaking, VCC Sense is the more accurate measure if you want to know the actual CPU core voltage. The difference measured between VCC Sense and Socket Sense will be larger the higher the load on the CPU. For our purpose, which is to figure out the CPU VF curve from the BIOS, we won't see much difference as the actual CPU load in the BIOS is around 5 to 6 amps. I just wanted to highlight this particular setting. For your own testing, just make sure to pick one of the two and stick with that throughout your testing. For real-world overclocking and real-world testing, I would suggest to stick with VCC Sense. The last topic I wanted to cover in this segment is the impact of motherboard auto rules on our voltages. Auto rules are automatic settings that help make the overclocking experience more simple and more straightforward. Typically, auto rules consist of pre-programmed settings that change depending on the changes that the user make in the BIOS. Examples include, when enabling XMP, the motherboard may adjust memory subtimings and memory controller voltages to ensure stability. When manual CPU overclocking, the motherboard may change the CPU VRM load line settings. Motherboards may unlock turbo boost parameters out of the box to provide the user with higher performance. While most of these auto rules are definitely very useful in helping to make the overclocking experience go more smoothly, they're not always perfectly tuned. In a lot of cases, you'll find that these auto rules are more focused in making it look stable and making your system boot up after an overclock than they are focused on running really healthy voltages. For example, I've seen motherboards adopt CPU voltage auto rules for ratios above the default maximum turbo ratio. If you're going through the process of finding the voltage frequency curve, You may think the CPU has factory fused settings for those ratios, even if they don't. So it's important to keep an eye out for these auto rules. Okay, let's move from theory to practice and try to figure out our CPU's VF curves. First up is the P-Core VF curve. We configure the BIOS with the following settings. Then we adjust the P-Core ratio item, save the settings, reboot back into the BIOS and check the CPU core voltage readout. We cycle through the P-Core ratios from 20x to 54x. Then we put the values into an Excel file and plot our very first VF curve. I would love to say that this is in fact our P-Core VF curve, but there's a caveat. As I mentioned before, every P-Core in our CPU has its own PLL and has its own VF curve. So technically I would have to do this process for every of the P-Cores in my CPU, and then I'd have 8 VF curves for 8 P-Cores. But that's a lot of work, so maybe I'll do that next time. Or how do YouTubers do this? If the video hits 1 million likes, I'll do it. Next up is the E-Core VF curve. We configure the BIOS with the following settings. Then we adjust the E-Core ratio item, save the settings, reboot back into the BIOS, check the CPU core voltage readout, and this doesn't quite work. As I mentioned before, it looks like the MSI BIOS is only loading one P-Core and not loading any of the E-cores. So we can't read out the voltage like this. However, we can do it in the operating system using hardware info. We just check the V-core field in the motherboard section. We cycle through the E-core ratios from 20x to 41x. Then we put the values into an Excel file and plot our second VF curve. As the 12700K has one E-core cluster of 4 cores, this is in fact our E-core VF curve. However, the same side note we made with the P-cores can be applied in the case of the 12900K. The 12900K has 2 clusters of E-cores, therefore it has 2 VF curves for each one of the clusters. Last up is the ring voltage frequency curve. We configure the BIOS with the following settings. Unfortunately, we cannot isolate the ring ratio from the CPU core ratio, as it appears the ring ratio is always equal to or lower than the CPU ratio. However, luckily, the ring requires a higher voltage than the P-core for the same frequency. So we can set the P-core ratio equal to the ring ratio, then read out the voltage in the BIOS in the very same way we did it for the P-cores. We cycle through the ring ratios from 20x to 49x. Then we put the values into an Excel file and plot our final VF curve. To end this deep dive in the Alder VF curve, let's have a look at the curves and do some analysis. There's a couple of things I want to highlight. First, for all VF curves, you can see there's a factory fused curve up to the maximum default turbo ratio. For the P-cores, that's up to 50x. For the E-cores, that's up to 38x. And for the ring, that's up to 46x. Higher ratios, by default, revert to the voltage of the highest predefined point. Second, you'll notice that at a given frequency, the voltage required for the different parts varies greatly. For example, for 3.8 GHz, the P-cores require 0.956 volt, the E-cores require 1.206 volt, and the ring requires 1.090 volt. Since all these parts are powered by the same VCC-IA voltage rail, if we were to set 3.8 GHz for everything, the voltage would be 1.206 volt. So we'd end up overvolting the P-cores and ring significantly. Third, you'll notice that the maximum factory fused voltage for the P-core and ring is the same, 1.36 volt. For the P-core, this is at 50x, and for the ring, this is at 46x. I don't know if this is by design. I didn't see anything in documentation that would suggest so I don't quite know how to elaborate on this. 4. When we program an adaptive voltage in the BIOS, it will map against the OC ratio. The OC ratio is the highest configured ratio in our system. Well, sort of. Here's where Intel's technical documentation diverges from the implementation by motherboard vendors. According to Intel's documentation, it is technically possible to program an adaptive voltage and associated OC ratio for both core and ring. So we could program the OC ratio for the cores to 55x and adaptive voltage to 1.45 volt, and program the OC ratio for the ring to 50x and its adaptive voltage of 1.4 volt. The VF curves of the cores and ring will then independently interpolate between 55x and 50x for the core and between 50x and 46x for the ring. Furthermore, Intel's specification also allows for a per-core adaptive voltage configuration. So we could program an adaptive voltage for a specific P-core or specific E-core, which would map against the OC ratio, so that 55x could map to a different voltage for every core in our CPU. And then every core would independently interpolate between 55x and 50x to figure out which voltage to set. Now, I don't know if we could also program the OC ratio for each core independently. I think so, but I'd need to look into it more closer. But if we could, that means we'd be able to define a target adaptive voltage for an OC ratio for each P-core separately, for each of the E-core clusters separately, and for the ring separately. On a 12700K, that would mean 10 independent VF curves. But in practical terms, that doesn't really matter. Here's where our VF curve story comes full circle, as at the end of the day, we know there's only one VCC-IA voltage rail that determines the voltage for P-core, E-core, and ring. The actual voltage will be the worst case scenario of all VF curves, and in most, if not all real-world overclocking scenarios, that worst case is the voltage required for our highest P-core ratio. Hence why on most motherboards, despite it being possible to configure an independent adaptive voltage for every P-core, every E-core cluster, and the ring, there's only one option to set the adaptive voltage. And the OC ratio is programmed as our highest P-core ratio. So in conclusion, when trying to figure out the adaptive voltage, just focus on the maximum ratio for your P-cores and let the CPU worry about all the other things. Returning to our overclocking strategy, we set an adaptive voltage of 1.375 volt, which is slightly higher than our default maximum voltage on the VF curve. We also increased the turbo ratio offset for the P-cores and the E-cores to +3 pins over the default ratios. That will push the P-core frequency up to 5.3 GHz and the E-core frequency up to 4.1 GHz. Upon entering the BIOS, in advanced mode, click XMP Profile 1. Then enter the overclocking settings menu. Set P-core ratio apply mode to turbo ratio offset. Set P-core turbo ratio offset value to +3. Set E-core ratio apply mode to turbo ratio offset. Set E-core turbo ratio offset value to +3. Set CPU core voltage mode to adaptive mode. Set CPU core voltage to 1.375. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. With the use of turbo ratio offsets, we finally see a significant improvement in the benchmark performance. We see the highest improvement in multi-threaded benchmarks with up to +13% in AI benchmark. But also our single-threaded workloads score significantly higher with up to 7.31% improvement in CPU-Z single-threaded. When running Prime 95 small FFTs with AVX enabled, the average CPU P-core clock is 4880 MHz and the average CPU E-core clock is 3890 MHz with 1.312 volts. The average CPU temperature is 100 degrees Celsius, the average VRM temperature is 54 degrees Celsius, and the maximum M.2 temperature is 54 degrees Celsius. The average CPU package power is 283 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 4988 MHz and the average CPU E-core clock is 3891 MHz with 1.357 volts. The average CPU temperature is 93 degrees Celsius, the average VRM temperature is 51 degrees Celsius, and the maximum M.2 temperature is 52 degrees Celsius. The average CPU package power is 262 watts. In our fourth overclocking strategy, we will pursue a manual overclock. We try to build on what we learned in the previous strategy with the turbo ratio offsets and pursue a little bit more megahertz. However, we quickly run into a couple of challenges. First, while 7 of our 8 P cores can run stably at 5.5 GHz, there's one core that can't quite do it. With the turbo ratio options, we can set the frequency for a certain number of active P cores, but we cannot pick which those cores are. So when the weaker core is active and pushed to 5.5 GHz, the system would crash. Intel does offer a feature called per core ratio limit, which allows us to restrict each P core to a maximum ratio. In our case, we could use this function to limit the weakest core to 5.4 GHz, while the other cores can go up to 5.5 GHz. Unfortunately, this option was not yet available in the beta BIOS I tested. So we're stuck at 5.4 GHz for a single threaded boost, but that's still 100 MHz higher than our previous strategy. Second, we can further increase the all P core frequency to 5.1 GHz, but then we're hitting the TJ max, or maximum temperature, of 100 degrees Celsius when stability testing. The root cause of the high temperature is the high CPU voltage, which is interpolated between the adaptive voltage of 1.425 volt at 54x and the Intel factory fused voltage of 1.36 volt at 50x. Unfortunately, by Intel design, there are no VF point configuration options to lower the voltage at specifically the 50x point, so we are not able to lower the all P core voltage and possibly reduce the temperature. Third, the E core frequency is already maxed out with a turbo boost ratio offset of +3, so we didn't make any further overclocking improvements. In the end, we settle for a manual overclock at 5.4 GHz for up to 3 active P cores, 5.3 GHz for up to 6 active P cores, and 5.1 GHz for up to 8 active P cores. Upon entering the BIOS, in advanced mode, click XMP Profile 1, then enter the overclocking settings menu. Set P core ratio apply mode to turbo ratio. Set numbers of P core of group 1 to 3. Set target P core turbo ratio group 1 to 54. Set numbers of P core of group 2 to 6. Set target P core turbo ratio group 2 to 53. Set numbers of P core of group 3 to 8. Set target P core turbo ratio group 3 to 51. Set E core ratio apply mode to turbo ratio offset. Set E core turbo ratio offset value to +3. Set CPU core voltage mode to adaptive mode. Set CPU core voltage to 1.425. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. After pursuing our final manual overclock, we achieved the best performance in all our benchmark applications. The highest performance gain is in AI benchmark, where we increased by 14.09%. When running Prime 95 small FFTs with AVX enabled, the average CPU P core clock is 4,871 MHz, and the average CPU E core clock is 3,890 MHz with 1.308 volts. The average CPU temperature is 100 degrees Celsius, the average VRM temperature is 54 degrees Celsius, and the maximum M.2 temperature is 55 degrees Celsius. The average CPU package power is 286 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P core clock is 5,082 MHz, and the average CPU E core clock is 3,890 MHz with 1.386 volts. The average CPU temperature is 99 degrees Celsius, the average VRM temperature is 53 degrees Celsius, and the maximum M.2 temperature is 54 degrees Celsius. The average CPU package power is 282 watts. Alright, let's wrap this up. When I put together this system, I had a couple of objectives. First, I wanted to check the overclocking experience with a Core i7 Alder Lake CPU. Second, I also wanted to check the cooling performance of the Z690 Carbon EKX motherboard. Thirdly, I also wanted to take this opportunity to have a deep dive in the topic of the VF curve. Overclocking the Core i7-12700K processor is not really that different from overclocking the Core i9-12900K. That said, this CPU wasn't the best one that I tested compared to the other Alder Lakes that I overclocked previously. I still managed to get 5.5 GHz on 7 out of the 8 P cores, and that's 200 MHz more than what I achieved with the Core i7-11700K and the Core i7-10700K. So that's still a great testimony to the overclocking headroom of Alder Lake in general. The Z690 Carbon EKX motherboard provided cooling in all the right places. The VRM and M.2 temperatures never exceeded 60 degrees Celsius, even when we pushed the system to its limits. People who are committed to custom loop liquid cooling and are looking to ensure thermal stability for their main M.2 drive will find a good use for the Z690 Carbon EKX. I thoroughly enjoyed exploring the VF curve topic in depth for this video. When you dig deep in the Intel technology, you realize there's so much more to it than what we usually limit ourselves to. I'm intrigued by some of the unanswered questions that came up during our testing and look forward to utilizing the information or the knowledge that we gained from the VF curve deep dive in future overclocks. Anyway, that's it for this video. In the coming weeks, I'll be putting up more Alder Lake overclocking content on this channel, so feel free to subscribe if you want to see more overclocking guides. For those who want to have a closer look at my BIOS settings or the results, I'll also put up a written version of this video on my blog. Of course, as per usual, if you have any questions or comments, feel free to drop them in the comment section below. And see you next time.